All right, let's jump right in. If you're building anything with AI right now, I'm talking semantic search, RAG systems, you name it, you've probably hit a fundamental question. How do we get a computer to actually understand what similar means? Well, today we're going deep on the one concept that makes it all work: vector similarity. This right here, this is the whole game. We take our data, words, sentences, even images, and we turn them into these numerical arrays called vectors. The real magic happens when we figure out which of these vectors are close to each other in this kind of crazy high-dimensional space. That closeness, that's how we measure meaning.
So how do we actually pull this off? How do we teach a machine to find related items or to rank search results in a way that actually makes sense? It all comes down to how we measure the relationships between these vectors.
Let's make this super concrete. Imagine all of your data points are like houses in a giant neighborhood. When a new query comes in, it's like a brand new house just got built. Our entire job is to find its nearest neighbors. This whole process, finding and ranking neighbors by how close they are, is the absolute engine that powers modern semantic search.
Okay, so to find those neighbors, we need a measuring tape, right? But here's the thing. In vector space, there's more than one kind of tape measure. And picking the right one is absolutely crucial. It really depends on what you're trying to do. So let's check out the main ones.
First up is L2 distance, or what you probably remember from school as Euclidean distance. This one's easy to picture. It's just the straight line, as the crow flies, distance between 2 points. If you have 2 dots on a map, L2 is just the length of the line you draw with a ruler to connect them. Simple as that. It's all about separation.
And then we have a totally different way of thinking about it: cosine similarity. With this one, we're basically throwing the ruler out the window. Instead, we're measuring the angle between 2 vectors. It could not care less how far apart they are. All it cares about is whether they're pointing in the same general direction.
And this is the core distinction, right? This is the fundamental choice you have to make. Is it about magnitude, how far apart are the endpoints? Or is it all about direction? Are they pointed the same way? See, 2 vectors could be miles apart, but if their angle is tiny, they'll have a super high cosine similarity. Getting this distinction is, well, it's everything.
Okay, so we've got 2 different tools in our toolbox. When do you use the ruler, and when do you pull out the protractor? Well, the decision really comes down to one critical and honestly often overlooked step you take with your data beforehand.
And that critical step is normalization. So what is it? Normalization is just the process of adjusting all of your vectors so they have a length of exactly 1. A good way to picture it is shrinking or stretching every single vector so that its tip just barely touches the surface of a perfect sphere. When you do that, you've completely taken magnitude out of the equation. The only thing left to compare is direction, which of course makes cosine similarity the perfect tool for the job.
So this table basically lays it all out for us. It's our cheat sheet. For things like text and finding semantic meaning, cosine similarity on normalized data is almost always what you want. Now, are there times when magnitude does matter? Sure. Maybe you're comparing images based on brightness, and a brighter image has a longer vector. In a specific case like that, L2 distance might actually give you a better result. But for finding concepts that are close, it's all about the direction. Oh, and dot product? Once you've normalized your data, it's basically the same thing as cosine similarity.
All right, let's cut through all the theory and get right to the practical stuff. If you're building a system today, what should you do? Well, there's a really clear, simple best practice to follow.
And here it is. It's this simple. Just 2 steps. First, normalize your embeddings. Make them all unit vectors. Second, use cosine similarity to find the nearest neighbors. Honestly, for the vast majority of semantic search and RAG apps out there, this 2-step combo is going to be your most robust and reliable path to getting great results.
So, seriously, let this be your default setting. When in doubt, just normalize and use cosine. There's a reason it's become the industry standard. It's because for tasks involving language and meaning, the direction of the vector, the concept it's pointing at, is just about always more important than how long it is.
At the end of the day, that's what we've really been talking about this whole time, this idea of similarity. Picking the right way to measure it, applying it correctly, that is the fundamental engine that drives all of modern information retrieval. It's how we find the signal in all the noise.
And that leaves us with this final question. Now that you've got the tools to measure meaning, what are you going to build? With all your data sitting there in this rich, complex vector space, the potential to uncover new connections, new insights, it's really limitless. So what meanings are just waiting there for you to find?